Good afternoon, everyone. So, in the last lecture, we started with fuzzy knowledge based system. So, what is a fuzzy knowledge based system? Yes. What are the components of a fuzzy knowledge based system? What are the blocks of a fuzzy knowledge based system?
One where it takes the crisp inputs, another it's
So,
like
the crisp input comes into the system, which is the first block,
Normalization.
normalization. Right. After that,
Fuzzification.
fuzzification. So, these are the steps actually. Okay. And then so it is divided into three parts. This is one part, input, there is some central entity, and then the third column is the output, right? So here from fuzzification it is having in the central part, right? So you can visualize it in this fashion, three blocks, and then there are sub blocks. Okay, what is there here? You have,
rule based or inference
yes,
system.
you have the database and you have the rule base. These two together form the knowledge base, right? And you have an inference system, right? An inference mechanism which is going to work upon all the rules which are saved in the uh, system rule base plus whatever database is. What is the database containing? What is the database containing? Something, some data. What data? The fuzzy sets which are used to model the inputs and the outputs. All those fuzzy sets are saved in the database. Okay? And any kind of conversion factors, scaling factors which are there as far as the normalization, denormalization is concerned, that is saved in the database. Right? So after fuzzification, what happens is inference takes place, right? And what is the right hand side?
Defuzzification and denormalization.
Yes, opposite of this, what is there here? So defuzzification and denormalization. So what does this inference system do? Inference system checks which of the rules in the rule base are fired, and accordingly it computes a output area. It computes the output. Okay, computes the output based on the rules which were fired, based on the input which the system had received. Based on the crisp input with which the system had received, the inference system actually computes the overall output. And that overall output is fuzzy because that comes in the then part of the rule. Right? So again, it's a fuzzy if then rule. So both sides are fuzzy. If part is that is the antecedent and the consequent. Both of them are fuzzy. So that output is fuzzy in nature. So you need to do the reverse process. You need to convert this fuzzy set back to a crisp value. right? And that process is nothing but defuzzification. The definition of defuzzification is conversion of a fuzzy set to a crisp value is nothing but defuzzification. Opposite process of fuzzification. Okay, and then it is denormalized. If you had applied a normalization block, it is denormalized to give you back the value in the range in the real world. A crisp value, crisp output value. So this is the architecture of a fuzzy knowledge based system which we had discussed in the last lecture. Okay. So today what we will do is we'll move ahead and we'll look at the defuzzification techniques which are there in the literature, and we'll solve one problem on defuzzification methods. Okay. So one by one, we'll just go through the defuzzification methods which are there, and then we'll solve a problem today, and then maybe one more next time, so that we get an understanding of how these defuzzification methods work. It is a process of converting a fuzzy set into a crisp value. And these are the defuzzification methods. I'll just list all of them. There are 8 different defuzzification methods which are available. So max membership principle, center of gravity or centroid, weighted average, mean of maximum, center of sums, center of largest area, first or last of maxima, and bisector methods. So there are 8 different defuzzification methods. We'll be discussing the formulae of each of these one by one. So the first one is the max membership principle or the height method. So this particular method is limited to peaked output functions. Okay, so whatever is the output function that you get, the output, who is going to give you the output function? Which block is going to give you the output function? The inference engine, right? The inference system, inference engine is going to give you the overall output. Okay, and this height method or the max membership principle method, what it does is it is suitable for peaked output function. That means where there is a peak, single peak. I mean, there could be multiple peaks, but there is one peak which is unique. Okay. So this is the algebraic expression for it. So that the value, the membership value, if there is there's a membership value which is greater than or equal to the membership values of all other x, then you can use this height method. And what is the graphical representation of this? So if this is the kind of landscape that you have, then by applying the max membership principle or the height method, the defuzzified value is the one which is shown here. That is this peak. This is the highest peak. So this is the defuzzified value by the height method. Now there are different variants of this height method. So like for example, if the peak is somewhat like this, it's not a single peak. It's not a single value, which is the highest value, right? There is a range. This is the peak for this particular region. This is the peak. Okay. And if you look at the x-axis, this is the x-axis. These are the x values. So there's a range of values. So there's a variant of the height method which you can use. We'll discuss that. That is called as the mean of max. method. Okay, so that variant is used in that case. So, but if there's a single peak, then if you apply this defuzzification method, then it's that X value which is giving the highest membership. Now, it is not necessary that the highest membership will always be 1, because the output, the overall output that you get, okay, from the inference engine, that might need not have this as 1 has as the maximum value. It can have anything in between 0 to 1. Okay, so it's not that it will always be 1. So that is what it is saying, that the clipped or scaled central output. So there are central outputs for each of these. So clipped, it's clipped actually. The region is actually clipped when you actually compute it using the fuzzy inference mechanism. There are different inference mechanisms that we'll discuss later, but it is not necessary that you will have it as 1. It can be 0.8 or 0.9, whatever it is. Okay. So just remember that when you're applying the height method, whatever is the highest peak, if there's a single peak in the overall output, and whatever is the membership value for that peak, that will be that particular X value. The X value corresponding to that will be the defuzzified value. Because defuzzification is you need X back, right? You have the this is the landscape. You need X back. You need to give X back, the crisp value back. So this is the defuzzified value. Now, one more thing is, this is the notation. So it is called as X star. When you defuzzify from a fuzzy set, when you obtain the crisp output back from the fuzzy set, you represent it by X star, the defuzzified value. Okay. Whatever the domain is, if it is Y, then it will be Y star. That is a notation for the defuzzified value. Next method that we have is the center of area or center of gravity or the centroid method. Okay, different names for the same method: center of area, center of gravity, or the centroid method. Okay, so what this does is you have to combine. So if you are having this overall output with you, whatever output that you have got, the combined membership output that you have, then you will consider that entire region, and you are going to find the centroid of that area. You're going to find the centroid of that area. So if there is something which is overlapping, so for example, you have these two regions. So if there is something which is overlapping, then that area is counted only once. It's not that you find the area of this and then you find the area of this and then you find the centroid and take the average, something like that. No, you look at the combined output region and find the centroid for that region. Okay, so how will you do it? You will simply multiply this with the membership value. So you will have to integrate it over it and then find it. When we solve the problem, it will be more clear. Okay, so basically what you have to do is you have to consider the entire area and you have to find find the centroid of that area. This is the formula for it. We will come back to it when we revisit the problem. So when we go to the problem, we will actually come back to this. And then this is computationally complex because it uses this integration. So it takes more time. It's a slow method. It takes more time because it makes use of integration. So whenever you are performing this integration operation, it will take more time. Because what you have to do is you ultimately have to find the area under the curve, right? So you know how to apply integration. So area under this curve, how will you divide this? So area under this, under this region, then area under this region, right? Like this. If you look at this particular region, what will you do? Area under this curve, this particular curve, right? Then this one, then this one, and then this one. Sorry. This one, and then this one. These are the areas which you need to compute actually. So it's computationally complex. That is why it is the output is a bit slower, but it gives you a better estimate of the defuzzified value because it is considering the entire output. It is considering the entire output which is given and trying to find the centroid. So although it is computationally complex, it is still giving you a fair idea of the defuzzified value. Okay, fair estimate basically. So that is about center of area or the centroid method. The next method is the center of sums method. So center of sums method, how is it different? It is faster. What it does is individual fuzzy sets, it finds the uh, area separately instead of taking the union of the entire landscape. So if you look at this particular area you're computing, this particular area you're computing separately. So individually, the fuzzy membership functions which are used, they are individually, the area is individually computed. So here you are not wasting time. So what happens, or what is a drawback of this is, this particular area, there's an overlap. So this is counted twice. So there's a problem with the estimate. Okay. So you take the overlapping areas into consideration here. Okay. So that is a drawback of this method, wherever there will be an overlap, right? There will be an overlap. So this area is counted twice. And because this area is counted twice, what happens is the estimated value, although it is faster, you don't have to break it up and do all that stuff what we did earlier. Just consider this area, and find out the area. Okay, it is faster. What we have to do is, the problem with this is that this is counted twice. So since it is counted twice, the estimate is slightly off, okay, for the defuzzified value. So that is a drawback of center of sums. So individual areas are computed and the centers are computed, and then overlapping areas are considered every time. So more than once they are reflected. So this is center of sums. Next is weighted average. So weighted average is valid for only symmetrical output functions. So if you have symmetrical, all your functions are symmetrical, then you can go for weighted average. Okay. And it is very simple. You need to just look at the center of the membership function and multiply with the weight or the membership values. Okay. So this particular value A, you will multiply with whatever is the peak value, that is 0.5, the center of that particular fuzzy set that you consider. This particular fuzzy set you will consider the center of it, B, you will multiply by this and find the weighted average. So you divide it by the sum of the memberships. So that is weighted average. So whenever you have a symmetrical output membership function, you can go for that. It is faster. Okay. Next is the mean max or the middle of max or mean of max. Okay. So this is the modification of the height function, height membership principle, which I was talking about. So if you have something like this, right? You have something like this where there is not a single peak value, but there will be a range of values for the peak. Then in that case, you apply this mean of max. Now, what you need to do is simply you need to take the average of these two values, right? So it is a plus b divided by 2. Okay, so what you do, you look at the lowest value here, you look at the highest value here. That means on the x-axis, you look at the lowest value here, you look at the highest value here, take the average of that. That is nothing but the mean of max. So this is yet another method that you have. Next is the center of largest area. What is center of largest area? So whenever you are having a non-convex fuzzy set as your output, if the area that you're considering is non-convex, then you use center of largest area. So what happens in this case is you have to actually divide your uh, region, your area, the non-convex area that you have, into convex fuzzy subsets. And out of these convex fuzzy subsets, whichever is that fuzzy subset which is having the largest area, that area center has to be considered as a defuzzified value. So if this is your non-convex area, right? This region is non-convex, right? So you divide it into convex regions and consider the that particular MF which is having the largest area to find the center. You find the center of that MF which is having the largest area from among the convex fuzzy subsets. Okay. So this is center of largest area. Next is first or last of maxima. So first or last of maxima is again from the height method. Okay. So basically, if this is it is a single peak, so then first of this is the maxima, right? This is the maxima. Maxima is a peak basically. So this is if there's a single peak, then the first of maxima is this value, and last of maxima is also this value. But if you have something like this, right? So here, what is the first of maxima and the last of maxima? This is the maxima, right? So what is the first of maxima? It is this value. If this is A and this is B, right? So first of maxima is A and last of maxima is B. Okay. So this is the first or last of maxima, this method. Then there is the bisector method. What is this bisector method? Bisector method is you use the vertical line that divides the region into two equal areas. Okay, so you consider the entire area and you find that line which is going to divide this particular area into two equal areas. Okay, so you have to equate them actually. So this area, this entire area should be equal to, that left area should be equal to right area. Okay, you have to find this line or this x value. So how will you find this? You need to integrate this. You want to find this area. So from this to this, let that is x star. Suppose this is A and this is B. From A to x star, you find the area. Okay, and from that is left area. Okay, that means this is the equation of this line. You have to break it up again. And from x star to b, you find right area. There'll be some equation. So this is a definite integral. So what you're going to do is a is there with you, b is there with you. This value is unknown. So you will get an equation in x here. You will get an equation in x here. So there's one unknown, right? One equation. You have to solve this equation basically. Once you solve this equation, you will get the x value or the x star value. And that x star value is nothing but the defuzzified value. So that is the bisector method. Okay. So you have to find that line which divides the region into two equal areas.
Ma'am, but in this case, how will we know that what area we have to consider in left and what we have to consider in right? Because we have to write the equations. No?
Just a minute. Probably you have to actually consider the entire area and then subtract something. I mean, because that equation is valid, you'll get two different equations. So let me see if I can solve some problem separately on this bisector of area. Okay, I'll get back to this because it involves equating. So this entire area, if you consider, and then probably use that equality there, then you should be able to get the equations so that you get the x value.
मैम इसमें एक ही अननोन वेरिएबल है ना, तो हो जाएगा ना ये इक्वेशन सॉल्व जो आपने लिखा है.
No, he is telling that I don't know that where to put that line na x.
वही तो इक्वेशन से पता चलेगा ना
वो
जो
तो
आपने
अज्यूम किया ना, एक्स स्टार तो
नहीं।
अज्यूम किया.
हाँ वही तो एक्स स्टार ही एक है जो अननोन वेरिएबल है वो तो पूरे इक्वेशन में.
इंटीग्रेशन के अंदर तुम लोग को एक इक्वेशन लिखना रहेगा ना.
वो एल ए और आर ए की बात कर रहा है.
हाँ तो वो एल ए और आर ए कहाँ तक
अच्छा वो
डिफाइंड है वो तो
हाँ, this range is like, I mean, this line, if you're considering, he's telling na the equation of this line will come na here. That is what you're trying to say, right, Harsh?
यस
The
मैम तो वो
equations you're telling na.
हाँ तो ज्योमेट्रिकली अभी दिख रहा है बट वो
Hmm.
लाइन कहाँ पे वो पता ही नहीं है ना.
हाँ, आप, I got your doubt. That is what I'm saying. So actually, I think I have solved this one of these problems. I'll discuss that with you. I'll come back to it. We'll
वो भी
solve it.
शायद वो एक्स स्टार के टर्म्स में होगा ना इक्वेशन दोनों.
हाँ, वो x स्टार के टर्म्स में होगा, लेकिन अरे देखो ना, यहाँ पे कहाँ तक जाना है आपको. See, your x star, I mean, if you break this up, so it will be a to some this point. This point is, say, some value. These are some values. Suppose it is 0 to 2, the equation of this line, right? Then this to this, but I don't know till
इसका
where
तो
to
वैल्यू
consider.
y इक्वल्स टू जो भी मेंबरशिप वैल्यू है वो होगा, क्योंकि वो ये लाइन है पैरेलल टू एक्स एक्सिस. मतलब पता नहीं, अभी वो आप सॉल्व करेंगे तो पता चलेगा, बट
हाँ,
मैं बोल
because
रहा
that
था
is a
कि
definite. हाँ, that is what
हाँ.
I also said initially, that there'll be one equation, one unknown, so you can solve it. But then his doubt, when we solve it, we'll come to know what exactly. Now, let's go back to that problem. Now, when I solve it, we'll come to that. Okay, Harsh will revisit it. Don't worry.
Yes.
So first problem we'll solve. These are the fuzzy sets which are given to you. Okay, you have to apply these methods which are given.
Ma'am,
So
is there any defuzzification method which does not work for non-convex areas?
um, all of them work non-convex areas. I'll have to check exactly which one. Right now, I'm not sure. Okay, so but more preference is given in the sense that whether you're going for a computationally intensive process or no. Okay, but if it is not working, then you cannot use it. Centroid method can be used. Weighted average can be used. Um, height method actually, okay, that also can be used, because if there are multiple peaks, yes, it works. I'll have to check on this, Sagar. I'll get back to you.
Yes, ma'am.
Yeah. So mean of max. So what you have to do first is you have to consider this entire region. So C1, C2, C3, you have to combine together and consider the combined region. Okay, so plot it on the same graph. So you take the union of all of this, plot it on the same graph. So this is the combined output region, and then you find the apply the techniques one by one.
Ma'am, can you go back 1 minute?
Yes.
Yes, ma'am.
Yeah. This is the combined region. Okay. So mean of max. So what is mean of max? Look at the max. This is the max value, max peak. Mean of max will be, it's not drawn properly, but it is, this is 6 and this is 7. Huh? This is 6 and this is 7. So mean of max is nothing but the average of 6 and 7, right? What is the defuzzified value? X star by mean of max is? It is 6.5, right? by mean of maximus. That is simple. Next is centroid. By centroid, what you have to do is you have to find the equations of each line, integrate it, and so there's an integration in the denominator and the numerator as well. So what you have to do is, this is the equation. So these integrations divided by another integral term. So it is very complex computation. So how will you proceed? You have to use the definite integrals here, right? How will you write? This particular, each of these lines you have to see and the area under that line. That is what you have to do. So what do you do? Definite integral starting from 0 to 1, right? So what is that mu of z? The equation of this line. What is the equation of this line? Can you tell me what is the equation of this line? Y is equal to mx plus c. There is no c. What is the equation? What is the mu value? Mu is equal to 0.3x.
Yes, ma'am.
Okay. Next is multiplied by x dx. This is the first integral. Next integral is, this is the numerator that I'm writing. Okay. Similarly, we'll write the denominator. So from 1 to which point? This point we have found. How did we find? This is intersecting. These two lines are intersecting. They are intersecting at this point. You know the equation of this line. You know the equation of this line. You can compute this value, right? So comes out to be 3.6. So from 1 to 3.6, equation of this line. What is the equation of this line? It's a constant, right? It's 0.3. Only 0.3. Yes or no? Okay, 0.3 multiplied by x dx. It's a straight line. Next, from 3.6 to 4. So from 3.6 to 4, the equation of this line. What is the equation of this line? What is it? You know now how to find the equation of the line? Yes, Harsh?
यस मैम वो कॉम्प्लिकेट हो रहा है डेसिमल्स में
Decimals?
0.5x.
ये line.
इंटरसेप्ट भी है ना उसका
हाँ. दिस लाइन मतलब ये पूरा लाइन है ना, ये पकड़ लो ना, ये लाइन का इक्वेशन सेम ही है ना. It is x minus 3 divided by Divide by what?
1, 4 minus 3.
4 minus 3.
x minus 3 by 2 है शायद, y equals to x minus 3 by 2.
X minus 3 by 2. Right. So x minus 3 by 2. ये है ना इंटरसेप्ट हर्ष?
हाँ, yes.
हाँ, ये नहीं है. Next. Into x, this will be multiplied by x times dx. Fine. Next is from 4 to this point, that is 5.5. Again, you have to find out this point. 4 to 5.5. This is a straight parallel line. So it is, equation is whatever is that, 0.5. Wherever it is cutting, 0.5. Mu is equal to 0.5, right? Next. From 5.5 to 6. Equation of this line. Now tell me, what is the equation of this line?
x minus 5.
Now that is 1. So x minus 5. Next, from 6 to 7. What is 6 to 7? Right. 6 to 7. It's a straight line. It is 1. And finally, 7 to 8. This negative slope is there. This line, the last line, what is the slope?
minus x plus 8 शायद.
Yes, 8 minus x. 8 minus x, and this is 1, so it is fine. Okay, so this is the numerator. So it is complex centroid method. What is the answer now? Add these integrations values. Definite integrals you have to use. पॉइंट 3 एक्स स्क्वायर है पहला. तो एक्स स्क्वायर का इंटीग्रल क्या है? x3/3. Right. So each of these integrals you have to evaluate, and then over that interval you substitute that value of that interval. What is this first one? It will take time to solve this problem. Okay, what is the first value? 0.3 x cube. Right? 3 you can take outside. Right or no? Integrations you know better. Then what you have to do? You just have to subtract this. 1/3 minus 0. You can remove this 3 out. So this is 0.1. So 1 minus 0. Correct? Next. X square by 2. Are you getting it? Okay, similarly, you have to write the denominator. Notice in the denominator there is no x. You only have that 0.3x. I mean these line values. Okay. 0 to 1, 1 to 3.6, right? Something like that.
मैम बट ये मतलब इंडिविजुअली होगा ना, न्यूमरेटर बाय डिनोमिनेटर प्लस न्यूमरेटर बाय डिनोमिनेटर?
नहीं, होल न्यूमरेटर डिवाइड बाय डिनोमिनेटर.
अच्छा,
पूरा न्यूमरेटर, इसलिए दैट इज व्हाट आई एम डूइंग. न्यूमरेटर पूरा कंप्यूट करो, डिनोमिनेटर पूरा कंप्यूट करो, एंड देन divide the two values. So I am writing the final answer here. You check whether you are getting it. You have got how to find it, right? That is important. You have to solve it. Maybe you can solve it at home. Complete this problem and verify the answer. The defuzzified value x star has to be 4.9. Okay. Next is center of sums. What is center of sums method? Center of sums, individual areas, overlap. Okay. So find the area of C1, find the area of C2, find the area of C3. So those three different fuzzy sets which were there, C1, C2, C3, find the area. Okay, so these are the areas. How did you find their shapes? Which this formula you know, na? Trapezoid and they are trapezoids. What is the area formula for trapezoid?
half into height into sum of parallel sides.
Yes. So that formula you have to apply. You will get the areas. You're getting it? Check half into 0.3 into for this particular trapezoid. What is it? Half into 0.3. Sum of the parallel sides. So this side is 1 to 4.
3 plus 5.
This is 1 to 5. 8. 2.4 into 0.5. What are you getting? 1.2. Right? That is 1.2. Similarly, you find for C2 and C3. Okay, so these are the areas. Then find the center of each individual fuzzy set. The center of C1, center of C2, center of C3. And then what you do is, what will you do? Again, you have a numerator and a denominator. So what you have to do here is, each area you multiply with the center and sum it up. So it will be 1.2 multiplied by 2.5 plus 1.5 multiplied by 5 plus 2 multiplied by 6.5. That will be the numerator. Denominator, what you will have is the sum of the areas. Okay, that is 1.2 plus 1.5 plus 2. So when you do this, you will get the defuzzified value. So defuzzified value, what are you getting? Numerator is multiply whatever is the numerator, denominator, you will get final value is 5. The defuzzified value that you get is 5. Okay. So this is center of sums. Next is check whether you're getting 5. Okay. Next is weighted average. What is weighted average method? Weighted average, all these actually these functions are symmetrical. Okay, so since they are symmetrical, you can apply weighted average. So C1, C2, C3 centers and the membership values are at these centers. C1, C2, C3 centers. What are the centers? Multiply with the corresponding membership values at those centers. Okay. Two 2.5 into 0.3. I mean, consider these individual. You're getting it, na? Weighted average. 2.5 into 0.3, 5 into 0.5 plus 6.5 into 1 divided by what? The membership values of the centers. Okay. So 0.3 plus 0.5 plus 1, the membership values of the centers. So this is the defuzzified value by weighted average. Right? Centers multiplied by the membership of the centers, sum of that divided by the sum of the membership values. That is the weighted average. And what are you getting by weighted average? You should get 5.146. This is the defuzzified value that you get.
मैम इसमें वो C2 5.5 होना चाहिए ना?
C2 5.5 है.
पिछले वाले में तो वही दिया था.
नहीं सेंटर सी ना.
ओके
हाँ, सेंटर इज 5.5 इसलिए लिया था, वो इंटीग्रेशन कर रहे थे उस पॉइंट तक ना, उस लाइन का, ये इधर से इधर तक.
यस मैम गॉट.
So this is, we'll stop here. Let us discuss the other methods, as you said, bisector methods, and also discuss about convexity and non-convexity in tomorrow's lecture. Okay, and we'll solve one more problem. Totally, I'll be solving it. Okay, you can solve along.